Okay, today we're happy to have Sam Homiller he's a postdoc at Harvard, and he's going to tell us about zero modes of massive fermions and axion strings.
All right. Yeah, so thanks very much for the invitation. So like John said, I'm going to be talking about this kind of fun field theory project that I did with a few other people here. So John Stout is a fellow postdoc here at Harvard, and Hengame and Katie are both excellent graduate students. Katie's actually just finished up and she's moving to Berkeley this fall. Yeah, so I'm going to be telling you this kind of neat story that we put together about the zero modes of axion strings in the situation where the PQ symmetry is explicitly broken. So you have these fermions that are everywhere massive, and yet in the presence of strings, you still get these zero modes that pop out and have some kind of interesting properties. And so hopefully I'll convince you guys that this is kind of some neat field theory with potentially some hopefully interesting future applications. Okay, so first, I'll just set the stage real quick. I mean, I'm sure all of you are quite familiar with all of this, but just so that we're all on the same page and speaking the same language. So I'm talking about axions, and to my mind, there's three reasons that axions draw a ton of attention, especially in the last 5-10 years or so, in the context of particle theory. So the first, of course, is the strong CP problem. And in case any of you hasn't heard about this, the idea is essentially that if you think about the standard model properly, the gauge theory, there's this additional parameter, the theta term, the coupling to GG dual, and the invariant combination theta bar plus the argument of the determinant of the quark mass matrix, is in principle just a measurable parameter. It's a phase. It should take on some value between 0 and 2 pi. And it also leads to an electric dipole moment for the neutron. And yet when we go and search for this electric dipole moment, we find that the value of theta bar that's experimentally allowed is smaller than 10 to the minus 10. And so there's this obvious massive fine-tuning problem here. And axions essentially promote this parameter to a dynamical field. And QCD dynamically generates a potential that minimizes this field at the origin, and so it really dynamically solves the strong CP problem. And this was kind of the original reason that people started thinking about axions. They started getting much more exciting when people realized that if you start with this, if you have this field that is kind of this extra theta parameter. Generically in the early universe, you're going to have some misalignment, and as the universe cools off, the axion will kind of roll to the bottom of the hill. It'll oscillate, and despite the fact that these axions are generally extremely light, this oscillating field behavior leads them to redshift like matter, and so they can actually potentially be either a component or all of the dark matter that we see. And so this idea of perhaps solving the strong CP problem and the dark matter problem in one go, is one of the reasons why I think axions are so popular to think about. And then the last motivation that I like to cite is of course string theory, or just kind of gauge theories in general. I mean, anytime you're thinking about gauge theories in extra dimensions, axions, especially in particular string models, just tend to arise copiously anytime you have some kind of compactification of a higher dimensional field. For example, a gauge field on a circle, can give you these light, essentially Goldstone bosons from the compactification. And so, if you actually were to observe an axion, it would be potentially this kind of interesting playground for understanding physics in the far UV, even by measuring the properties of this very light field. Okay. Yeah, so that's just in a broad brush why everybody is so excited about axions. The main property of axions that I'm going to be talking about today, and the reason that they're kind of connected to what I'm going to be saying, is that they really, I mean, when you think about an axion, as opposed to an arbitrary Goldstone boson or pseudo Goldstone boson, you should think of an axion as a scalar field that intrinsically, by definition, has a periodic field range. And so it really is, a field that has a discrete gauge symmetry where you identify this field theta and theta plus 2 pi. And so here I'm working where this field is dimensionless. You could always, divide out the axion decay constant, and then the period would be 2 pi f for the axion decay constant, but that doesn't really make much difference for what I'm going to be talking about. But so the fact that they have this periodic field range makes them, in the context of field theory, kind of just intrinsically connected to interesting topological notions. And they derive a lot of their interesting properties from their interactions with topological defects. And these interactions just lead to a bunch of kind of interesting stuff and change their phenomenology in really dramatic ways. The first, oldest way that we all understood, of course, was, they couple to Yang-Mills instantons. They give contributions to the axion potential that's in a way related to the story of how they solve the strong CP problem. And as my friends here at Harvard pointed out, in the context of abelian gauge theory, due to the Witten effect, magnetic monopoles also give a contribution to the axion potential. And you can think of this as arising from loops involving those magnetic monopoles, as long as those magnetic monopoles exist anywhere in the spectrum, regardless of whether or not they're actually populated in the universe. And so these are two, just fundamental kind of topological defects that can change what the axion potential looks like. And the last one here is the thing that I'm going to be mostly focused on, is that axions, models with axions just generically have string and domain law solutions. And these are really, really important for understanding kind of the cosmological history of axions. And I'll give a couple kind of concrete examples about that as I go along. Okay. So now first I want to describe, the very, very basic setup of axion strings and kind of the simplest picture of it that I can possibly draw. And hopefully convince you why that these axion strings are really potentially really interesting and important for cosmology. So the simplest setup I can come up with is just to write down phi to the fourth theory with a complex scalar I'm going to call capital phi. I'll give it a potential that spontaneously breaks. So it's a complex scalar. It has a U1 symmetry where you just rotate the phase of this guy. I give it a potential that spontaneously breaks this symmetry. And here I can identify the axion field as the argument of this complex scalar, right? So just the phase that sits in this complex field is the axion field, and you can see that classically this is just the Nambu-Goldstone boson that comes from the spontaneous symmetry breaking here of the U1. All right. So you can think about this in the regular vacuum where you just have this massless Goldstone boson here. But what becomes more interesting is that this very, very simple theory, in addition to the normal vacuum, admits string solutions. And so these are classical field configurations where the scalar field has some non-trivial winding. So I center this at the origin, call the radial coordinate r, and I imagine that the scalar field, the classical profile of this field, is such that n here is some integer, and as I go around the origin, the field value winds once, and then it comes back. And so it's, it has this non-trivial topology built into it. And then the modulus is just characterized by this function f, which you can solve by just plugging in the equations of motion, minimizing the energy, and solving for this scalar profile. And an important point is that these field configurations, while they are not the minimum energy solutions to the equations of motion, they are topologically stable, right? I mean, if I'm working in this background, no small fluctuations of the field can take me out of this topological sector into another one. For any of these integers n, each of them are distinct. And so I can work in this string background and consider that as my kind of background vacuum as opposed to the trivial vacuum. I should say, in contrast to what you might have studied, gauge vortices in the context of gauge theory, and those you also have a gauge field, and that gauge field takes some non-trivial winding and kind of eats up some of this winding too. Those gauge vortices are they do not have a logarithmic tension. These axion solutions, there is no gauge winding. It's just the scalar field that has some complex winding. And so they actually are logarithmically divergent if you compute the tension. But this is not really a problem. You can think about if you really want to regulate this IR divergence, you can imagine just having the string go in a giant loop with some large radius r, or you can have, a string at the origin and a string with the opposite orientation sitting at some large distance. These are really kind of equivalent things. And in the context of cosmology, as we'll discuss in a sec, you're generally going to have, big networks of all of these strings. And so the IR divergence is always cut off by the fact that you have other strings nearby at some point. And so I can just think of this as an interesting background that I can think about in my theory. All right. So here, as I hinted, these strings can be very important phenomenologically, and when you're thinking about the cosmological history of the early universe. And in case you have never seen this before, here's just kind of a cartoon of how this kind of works. So you imagine at high temperatures, the potential that the scalar field feels at very, very high temperatures, that you get this extra temperature-dependent term. All of the fields are stuck at the origin, and then as the universe expands, the temperature cools. You can imagine the scalar field in different patches, starts to relax and come down. And then at some point, the scalar field is going to roll down to its minimum at the bottom of the potential. But it doesn't necessarily have to roll to the minimum of the potential at the same place in theta in the argument at every point in space-time, right, across space. So as this happens, you're going to get different patches of the universe that have the scalar field essentially they're all going to take the same modulus v that minimizes the potential, but the phase is going to take different values in different patches across the universe. And now you have to have, the full scalar field that, goes throughout space-time has to interpolate between all of these different things. And sometimes that's relatively trivial. But just generically, you're going to get these patches where there is this intrinsic winding that you have to have with this interpolation. And so that leads to the formation cosmologically of all of these strings that you can see. And here it's just kind of to wrap around this particular point, and the field of value is taking different values. You have to have a string solution here to smoothly interpolate between all of these. Okay. So this is what's known as the Kibble-Zurich mechanism. It's been understood for decades, of course, now. And actually, you can see this. I mean, we assume that this happens cosmologically, and it's very important. But you can also actually observe precisely this mechanism happening in superfluid helium. And so this is not, completely groundless theoretical mumblings. This is, a thing that we kind of understand about field theory. And then what's kind of neat is that, again, you're going to have this happen in all of these different patches all over the universe. And so you're going to get these strings, at all of these different points, and you're going to have this large network of strings. And these strings, are moving around. They can travel, essentially at the speed of light. And then they can interact each other. They can cross, they can form loops. And so you have all of these nonlinear effects in cosmology, and you can really only study these carefully with large-scale simulations. And there's been a ton of work in the last couple decades, especially on really understanding the cosmological evolution of these in particular. But what's been understood for a long time is that the sum of all of these different nonlinear interactions leads to this interesting scaling behavior. And so while an individual string, it has a tension and its energy density is not going to redshift in any kind of particular way, these networks of strings, because they can form loops and collapse and cross each other, they generically approach the scaling solution, where they essentially, even as the universe cools, the energy density in the network of strings approaches a constant. And so you can have this stable energy density of strings. And now these things can radiate axions, and that can influence the primordial axion abundance that you expect in your theory. So understanding all of their interactions and all of this is clearly very interesting, if for nothing else, to think about, what the primordial abundance of axions might be. Okay, so that's all in this very, very simple story where I just have a complex scalar field, and all of that goes through. Everything becomes much, much more interesting if I really start thinking about models of axions properly. And so I'm going to take this theory that I had where my complex scalar is here, and now I'm just going to add spinor electrodynamics. So I add a new fermion here, an abelian gauge field, and I'm going to give this fermion a chiral coupling to the scalar field here. So phi1 and phi2 are just the real and imaginary parts of the complex scalar, but I put this gamma 5 in here, so that now this U1 symmetry that I had before that acts on the scalar is still a symmetry if I have it act chirally on the fermion fields. So as long as I do these two rotations together, this is still a U1 symmetry of the theory. And of course, classically, this is a perfectly fine global symmetry. But at the quantum level, of course, the symmetry suffers a chiral anomaly. And so, you get this extra FF dual piece in the theory. And so if I expanded this piece, this interaction between the fermion and the scalar here, you would see in the classical Lagrangian an interaction directly between the axion field and psi bar. That you would have this axion coupling to fermions. You can perform a chiral rotation of the fields to remove that fermion coupling. But because of this anomaly, doing that rotation, it doesn't preserve the Lagrangian. You introduce a coupling of the axion to FF dual, right? And I'll come back and talk about this FF dual coupling a lot, of course, in what follows. Okay. And so this is this is the stage that I'm mostly going to be considering for the rest of the talk. Is this context of axion strings and electrodynamics. And it's been well understood since the 80s that in the string background, as I'll prove in more detail than you probably ever wanted to see about classical axion electrodynamics, these fermions emit chiral zero modes that are affixed that are localized to the string and travel along the string with a fixed helicity. And as I'll show you, these fermions, these chiral zero modes exist. And along the string, they move at the speed of light, and they carry charge because the fermions are charged under E and M. And so the string essentially becomes, it becomes a superconducting wire. It has charge carriers that lie on the string. There's no dispersion. And so if you put this thing into an electric field, it's just going to build up a current linearly, and there's no resistance. They really are just superconductors. Okay. And this has a bunch of interesting kind of phenomenological consequences that have really, I think, only been even though this fact that the axion strings are superconducting has been known for 40 years, there's been a lot of revisiting this just in the last few years about kind of how this can influence phenomenology. So the first important point is that because the superconducting axion string, it has these fermion zero modes it's superconducting, it can experience a drag force if the string is moving around in a plasma of charged standard model fields. And so this changes the way that these string networks evolve. And it turns out it actually enhances the number of axions that are radiated by these networks as they move through cosmology. And so here I've just put a couple of relatively recent references showing that in large scale simulations. The other thing that can happen, just as an example, is that in the presence of some primordial magnetic field, if one of these strings is just moving through this primordial magnetic field, because it has these zero modes, it can start charging up the strings. And now you essentially just have these, standard model like fermions that are moving along the string at extremely high speeds. It can cross through, other plasma of standard model particles and create, essentially collider signatures almost from these strings moving through the early universe. So clearly, it's worthwhile to kind of understand all of the physics of these chiral zero modes, where these are really coming from, so that we can make sure we really properly understand all of the phenomenology, because it can be kind of important. Okay. So for the next couple slides, I'm going to walk through in excruciating detail why these zero modes on axion strings exist. And so I'll do this in two kind of parallel, orthogonal, but and seemingly unrelated kind of ways, show that these chiral zero modes have to exist. So the first is to just look at the fermion equations of motion directly. So I just write out the fermion equation of motion, and it's just a little bit of algebra that I'm skipping here, but essentially you just search for solutions that have definite helicity, that are traveling along the z-axis where I've put the string, at the speed of light. So I take my fermion field, I write down this ansatz that looks like this, moving at the speed of light. I have this fixed helicity that I can take to be plus or minus. And now I solve for the profile of this fermion, and so that's going to be capital F for the rest of the talk. You plug this into the equations of motion, and you find that f of r is up to some normalization factor that you have to fix, just this exponential related to the scalar field profile here, right? But for these to be solutions and be really zero modes, they have to be normalizable, right? I mean, that's the one other condition is I write this in, and then I ask that F has to actually satisfy a normalization condition for these to be really particle solutions to the field equations. And so that picks out the minus sign in this exponent here. And this plus minus here is correlated with the plus minus here. Yeah, sorry, go ahead.
Yeah, so is the small f of r here still looks the same as the one you showed in the previous slide? Like,
yeah, that's right. So lowercase f is always going to be the scalar profile, and capital F will always be the fermion profile connected to the string.
So at the location of the string, the axion field actually have value 0 because small f have 0 at r equals 0.
Well, but it's in the exponent, so it would be a 1.
Oh, wait. Oh, I see. So the axion is the small phi on the exponent. I see. Okay.
Sorry. The axion, yeah, sorry. Maybe I should have clarified here. So I flipped to, I mean, I'm calling them axion strings. And so you can think about the axion as the complex, the phase component of the string profile. So when I'm talking about it as a particle, as a field that has excitations, I'll call it theta of x. But usually I'm just going to be working in the string background, where that's phi is just the angular coordinate that is traveling around the string. And so that var phi is, I mean, I identify it essentially with the axion field, but I'm working in the background. And so there are no excitations of the axion. It's just kind of, you have this classical field configuration where the scalar field winds around. So I'll kind of use phi and theta interchangeably for the axion as I go. Yeah, but so the scalar field, the complex scalar has a profile that looks like this. Well, I think I already showed it. It looks like this. It approaches V at large distances, but goes to 0 at the core of the string. And so then the fermions are localized at the core because they just follow that string profile. Yeah, I'll come back and I'll show lots of plots of this in just a minute too.
Okay.
Yeah, great. Yeah, so like I said, so the only other thing once you've put down this ansatz that you require is that this mode has to be normalizable, which tells you that you have to pick the minus sign here, which means you have to pick the minus sign here. And so that really is telling you that when you write down these string solutions, you pick a definite orientation where the string is winding in a certain direction, and that picks out the chirality of the 0 modes that lie along the string. And you can see that just from the equations of motion. Okay. But since this is, I mean, so in principle, this is just showing you, like here, I've solved for the fermion 0 modes. But because this is really kind of crucial, I'm going to go into this at even more detail and convince you that you can really prove from the differential equations that these 0 modes exist. And this kind of intuition you get here will hopefully be useful in a little bit when we come to the massive case. So if I look at the differential equation I get for the string profile more closely, I write it out and it looks like this. And now what I'm going to do is I'm going to take this differential equation and I'm going to consider it in 2 different asymptotic regimes. So first, I look close to the origin. So near the core of the string, f goes to 0. And so then I can look at this differential equation and schematically, asymptotically, it has to just look like this. And this is a very, very simple, second order ordinary differential equation. It has 2 linearly independent solutions that have to just approach C1 and C2 R squared, right? And very importantly, both of these solutions are regular functions due to the smoothness of the string profile as it goes towards the core. But the second order differential equation has 2 linearly independent solutions, and I have one asymptotics is that it has to approach these 2 of these functions have to approach these. Now that was then at the core. Now I look at large distances, and at large distances, essentially this piece doesn't really matter because I'm taking R to be far, far away, and the string profile just kind of flattens out. On the other hand, the profile flattens out to a constant value V, and I should have noted it already here, but this mu here is just what I'm calling Y times V. So that's the mass that the fermions see far away from the string. So in the classical vacuum, the trivial vacuum, that would just be the mass of the fermions everywhere. from the spontaneous symmetry breaking. So now the differential equation just looks like this. This, of course, just has normal exponential solutions. Again, I have two linearly independent solutions, but now I'm forced to pick, again, a solution that's normalizable. And so I pick the one that asymptotes to C minus. And then the question is just, can I write down a function, a solution to this differential equation that interpolates from this function to some linear combination of these two across, all values of R. And then I know from the fact that this is a second order differential equation that then this has to exist. So then since you have these two solutions, there's always going to be some linear mapping between them. And so I can just write this, if I write F minus as the function, the solution that asymptotes to this, I just know it has to be some linear combination of the two functions that asymptote to these. And this is guaranteed to exist in this case because both F1 and F2 are regular at the origin, right? So the way that this could have worked is that if only one of these solutions was not regular at the origin, and the one solution that actually existed was this guy, but then it's connected to the solution that's not regular, then you wouldn't, the solution could kind of break down in the zero mode, this profile you wouldn't necessarily have a zero mode solution that works. But in this case, both of these things are regular because of the shape of the string profile. And so it is guaranteed that this solution to the equations of motion exists. Okay, good. So that was all of the detail I can possibly give about the chiral zero modes in this case, just from the equations of motion. And now you can just solve for this. You can't do it analytically, but you can. It's relatively straightforward to solve these equations numerically. And what you get is here. So here I think I showed it already. Here is the string profile is in blue. And again, it approaches some asymptotic value v at long distances and goes to 0 at the origin. And now I have the zero mode profile that's 1, it's localized about the origin. So it's 1 at the origin and goes to 0 at large distances. And now, I've kind of come around and said this a couple times, but I think essentially you can look at these solutions and get a sort of heuristic picture that when you have this PQ symmetry, it spontaneously breaks from the scalar field. The fermion acquires the mass from all of the fermion mass in the trivial vacuum comes from this chiral Yukawa coupling, right? The scalar takes some vacuum expectation value. You just get YV, psi bar, call that mu. And so that's where the fermion mass is coming from. And so this heuristic picture is that you have these massless zero modes that exist because the string core approaches 0 at 0. And so there the fermions are massless. And so of course these, it makes sense that you have these massless excitations at the core of 0 because there's no mass there. This cartoon picture of why these zero modes exist is good insofar as it goes. But I think hopefully I've kind of emphasized from doing these derivations that this is not exactly why the zero modes exist. And my goal essentially for the rest of this talk is to show you that at the very least, this heuristic picture is at best incomplete as to understanding whether or not you can have these zero modes. Okay. All right. So first, let me give you one other analogy and explain why this kind of intuition that, oh, the mass goes to 0 here, and that's why you expect to have zero modes localized there, is not a crazy intuition to have. There is a different example where that's exactly what goes on. So instead, consider the Dirac equation in 2 + 1 dimensions, where I take the fermion mass to be some monotonic function, m of x. And so that you can imagine, I could write down a scalar field theory where this, you have the scalar have a kind of domain wall solution. But here, for this example, really all I have to have is that I take m of x to be the mass that varies spatially, monotonically as a function of x. And so here again, I can search for zero mode solutions propagating along this domain wall essentially. So I write down my ansatz for what these look like. I get this differential equation. And now I do the same kind of thing, right? I look in the 2 different asymptotic regimes. Now it's not 0 and infinity, it's minus infinity and plus infinity. And in both of these regimes, I'm just going to have the mass approach some constant value. And so I have, again, just these 2 exponential functions in both regimes. But now, again, I have to make sure that these are normalizable. And in this case, if I actually want to connect the normalizable solution here to the normalizable solution here, again, this mass is varying as from minus m to plus m. To make these solutions match on, you have to have this mass value approach opposite values at plus or minus infinity for x, right? And in other words, the mass has to vanish somewhere. And then when you solve the equations of motion, that is precisely where the zero modes are localized. So this is, a reasonable story in the case of domain walls, that you get the zero modes essentially. I mean, it works both. I mean, the mass has to vanish somewhere, and that is why the zero modes exist. But again, this is coming from arguing about the asymptotic solutions and whether or not the solution you can construct is normalizable, not about the actual value of the mass. So this is really more of a topological argument as opposed to an argument about the mass itself. Okay. And it turns out, as was discovered by Cowan and Harvey in the 80s, that there's a topological explanation for why the zero modes of the Axion string exist as well. But it's a lot more subtle and interesting, and it has to do with the gauge theory. So what Cowan and Harvey did is they take the massive fermions, so that the fermions, again, at large distances far away from the string, they acquire a mass. And so now I can integrate them out of the theory. And if I do this far away from the string, that's totally fine. Near the string, I don't know exactly what's going to happen. And for now, I'm just going to ignore it, ignore any possible things that might happen there, and just see what happens to the theory, right? So once I integrate out the fermions, I get this effective field theory. We're now, I integrate integrate out the fermions and just work in the scalar field background. And so I have this kinetic term for the axions, my normal gauge kinetic term, and then this term that I get from the anomaly, the chiral anomaly, right? And this is the same thing that I said earlier, that you get it, you have this chiral coupling to the axion to the fermions. I can convert that into this. I could also think about just generating this term by integrating out the fermions directly in a loop diagram, right? And I would get the same theta term here. But it's this theta term that leads to some kind of subtleties. And so now I have this EFT. I'm going to ask, I started with a gauge invariant theory, and I'm going to ask, okay, what do I have to have for this theory to remain gauge invariant in the EFT, in the IR? All right. So I just take this EFT and I perform a gauge transformation, and I'm going to switch to using differential form notation here, but you could go back and work all of this out in detail if you wish. So first, I'm taking this gauge variation. First, I'm just going to take partially integrate this thing and convert this one of these f's to a d theta wedge a. And then I perform the gauge transformation, and I find that it's this. And now I integrate by parts once again, and I get this last term here that's d squared theta wedge the gauge parameter times f. Okay. And the first time you do this, you look at this and you say, good. If I know my differential forms, d squared on anything is going to be 0. And then I would find that the theory is gauge invariant. But that is not true in the contexts where you have winding. And winding, you're not on a regular manifold. And so this d squared of the theta is not 0, precisely because of these windings. So it comes out to be, I think, 4 pi. And essentially what you find then, because of this winding, you see that the EFT it seems like it has a gauge anomaly. I wanted this thing to be gauge invariant, and I find that, I take a gauge variation, a local gauge transformation, and it's not gauge invariant. And so what happens, and this is what Cowan and Harvey pointed out, is that this anomaly that you find, if you're very careful, and it does take a lot of work to make sure that you get all of the factors of 2 correct, is that this anomaly is exactly equal and opposite to the gauge anomaly that you have for chiral fermions in 1+1 dimensions. And so if I add to my effective field theory chiral fermions that can move just along the string in 1+1 dimensions, they have equal and opposite gauge anomaly. And so then the whole theory is consistent, gauge invariant is preserved. And really you require that these chiral fermions exist along the string for consistency of the effective field theory. Right. And again, I said this was a topological argument, and that's because it all comes down to this fact that, I have a non-trivial topology where d squared theta is not equal to 0. Okay, good. Great. So this was, all of the details about why, in this minimal model that the Cowan and Harvey worked with 40 years ago now, there are chiral zero modes that move along the Axion string. And for the rest of this talk, I'm going to kind of move beyond this minimal model by taking the first kind of simplest, smallest step I can think of to take away from this minimal theory, and that's by adding a mass that breaks the PQ symmetry explicitly. But just to motivate this a little bit more, there's a few reasons why you might want to think about how this story might change going beyond this simplest phenomenological model. One, and the reason that we originally started thinking about this is if you think about UV completions for the QCD axion, one of these is what's called the DFSZ model. Essentially, this is a model with two Higgs doublets and an extra complex scalar field. The axion is some linear combination of the pseudoscalars and all of those scalar fields. But because this model has additional scalars, there's several different, there's not just this one string solution that you can write down, indexed by the winding. There's several distinct string configurations that you can have. Some of these, and these have kind of interesting properties. Some of them are kind of electroweak strings where you preserve different subgroups of electroweak symmetry at the core. And there is other, there's these other papers, one of them I cited here, that argued that these strings are still superconducting. And so you can have these kind of interesting phenomenology in these models that's somewhat non-minimal. But if you look at these string solutions, none of the scalar profiles of these string solutions actually vanish at the core. And when we still kind of have arguments that they're superconducting anyway. And so it's not obvious if you kind of buy this heuristic picture, if none of those scalar profiles vanish at the core, it's not obvious why these zero modes might continue to exist. So that was the first reason that we started thinking about this. But the other reason that I think we were kind of interested in this question is in the background of a standard model plasma, fermions kind of generically, if you have a Dirac fermion, even if you have some global symmetry, they can acquire a Debye mass that breaks the global symmetry. And at high temperatures, you expect this Debye mass to break superconductivity, and the whole theory might kind of change, and you might have a phase transition as you cross some critical temperature. So we wanted to have a minimal model where you could try to study that in the future. And so the last thing I'll say here is, well, with the global symmetry, I can write down a small mass term that breaks the global symmetry. And yet, if I think about it, like the theory still seems like it's perturbative for very small Dirac masses. And so there's this kind of puzzle of, how are the underlying degrees of freedom moving around for this whole picture, and then what actually happens as I dial the value of this mass term. So the simplest first step, that's what I'm going to do, is just take the same theory that I had and add an explicit symmetry breaking mass term, right? So I'm just going to have the exact same Lagrangian I had before, but now add m psi bar psi. Okay. All right. So now I'm going to first kind of do a perturbative analysis of the equations of motion for small values of m, and study the solutions and see if these zero modes continue to exist. So if I work perturbatively in this small parameter m over mu, where again, this is the Yukawa mass far away, here's my equation of motion now with the additional mass term. And I'm going to look for solutions that are just like before, but now I add this small variation to these things, right? I can expand this equation in Fourier modes, and there's all of the different components of the fermion, but essentially all of these equations of motion just reduce down to a set of two nonlinear equations for these two extra string profiles, G and H, that are just the variation of this for the L equals 1 piece in the Fourier expansion for psi 0 and psi 3, right? So it's still kind of has the same sort of definite helicity structure. I can write down these coupled equations for these guys. And now I'm going to do the same game. I apply some asymptotic analysis to these two profiles, G and H. But if I do it, all of the details are in our paper. I'm not going to bore you with pages and pages of equations. But essentially what happens is the string leads to a regular singularity as you approach the origin. And so again, I have this interesting singularity, but I can match the two regions again. And again, I can construct a normalizable solution. And essentially the story just goes through exactly the same way that it did for the massless case. So I can construct this normalizable profile solution for G. And now once I have G, I look back at these equations and I can just construct a solution for H by applying this. And you might look at this and immediately get worried because I have a 1 over r here, I have another derivative, and I have f in the denominator. And so it's not obvious that this whole thing is going to break down and I'm not going to run into some kind of singularity and find an actual normalizable solution for H. But we demonstrated in our paper that if you just examine these, yeah, sorry, go ahead.
Sorry, I'm still at F. What is G and H?
Oh, sorry, yeah. So in the absence, so I'm working perturbatively in M, and so in the absence of G and H, so in the absence of F, this is exactly the solution we found before. So F is that same profile that's localized at the origin. And now I'm working to linear order in the small mass parameter. And so I have my solution is, I've just written my normal solution, and now I'm just working in perturbation theory. So it's the solutions for the deviations of this wave function in the spinner. Does that make sense? And I've just called them G and H here.
All right, thanks.
Yeah, good. So you can apply this asymptotic analysis, and if you're very careful, you find that these things, these singularities kind of magically, I mean, it's not really magic, but it looks like magic. The singularities cancel out, and in the same exact way as you did before, you can demonstrate that there is generically a normalizable solution for G and H that's still generically allowed. And so for small values of the mass, at least, I've just, this is just an argument that perturbatively, all of this goes through, and the existence uniqueness theorem of a second order partial differential or ordinary differential equation tells you that these zero modes still have to exist, and they just have these small changes to their profiles. So the zero modes, even when I add this small PQ breaking mass, the zero modes still exist. That's interesting. But now I can ask, okay, what's going to happen as I tune this mass to larger and larger values, right? I mean, if I take this mass to be infinitely large, then I don't expect the fermions to ever care about the string whatsoever, right? I mean, if there's some small string that has, interactions with the fermion, but the fermions are super, super heavy, who cares about the string, right? They're just going to be massive fermions everywhere, maybe with some tiny interactions along these things that are kind of irrelevant. And so there has to be some transition at some point between this perturbative value and this infinitely heavy fermions. And so how does this work? First, I mean, this picture that I gave you for this asymptotic analysis is not particularly illuminating, but I can give you another analogy, again appealing to a domain wall, as to why it sort of makes sense that these solutions might still exist. So now I'm going to consider the same kind of domain wall again in 2+1 dimensions. But now I'm just, instead of having the domain wall approach a positive m at plus infinity and minus m at minus infinity, I'm just going to restrict to the half plane and only think about the theory for x greater than 0. So assume there's some giant instruction that just keeps me from, I can never go to negative values of x. And so then I can just study the ordinary Dirac equation for this. And now again, I can search for zero mode solutions propagating along the z direction. They have the same form that I wrote down before. And now they're, sorry, this mu here should be an m. But now their differential equation is particularly simple. But now things are actually, I mean, it's almost trivial the way that things work out. If I look at these two regimes, small x, this equation for small values of x, it just gives me, there are two linearly independent solutions, but they're just two different constant values. It has to approach one of two different constants. And at large values of x, I again have these exponential solutions, and I have to pick the one that falls off so that this thing is normalizable. But since both solutions at x goes to 0 are always regular, they're just constants, the solution decaying at infinity is always normalizable. And so despite the fact that nowhere in this half plane is the mass 0, I am allowed to have these normalizable zero modes that are just confined to the boundary of this half plane, and that they can travel at the speed of light. So they act as though they're fermions with zero dispersion, despite the fact that the mass is everywhere non-zero. And I think you really kind of can think about this as analogous to the string core. If you just think of the core in cylindrical coordinates as, the boundary of the x-axis. And so this is just, moving far away. And it approaches some value where there still is a mass at the core, but I can still have these zero modes that are confined to that point. Okay, so that's hopefully some intuition to why the fact that these zero modes exist is maybe not too surprising. But I can also, I mean, I had two arguments for why the zero modes existed in the massless case. So let's see what happens with the other one. So I go back to this anomaly inflow story from Cowan and Harvey again, and I'm just going to do it again in the case where there's a mass, and I just have to be a little bit more careful about what exactly the chiral rotation I do is. So in the string background, my Lagrangian, the relevant part for the fermions looks like this. And so again, I have the Axion field here, the string profile, but I have the mass. And so I'm really interested in the path integral that I can write in this form. And here what I've done is I've taken this m minus y f e to the I gamma 5 theta piece, and I've rewritten that whole thing as one complex mass term that has an argument in a phase. And so you can just solve for what the argument of it is. I'm going to call that capital M. And what the phase is, I'm going to call alpha. Those are generic functions of r and theta. And so now once I've done this, so I can solve for what those values are. So M is this complicated function involving the math little m and y and f. And alpha is the argument of this whole thing that I could write in this form. Once I do that, I can just perform this path integral. I can write it as a functional determinant. Here I've just introduced some Pauli-Villar's regulator. That's not that important. But now once I've packaged these things in this form, it's kind of clear what the next step is to take. I just perform a field-dependent chiral rotation to get rid of this phase, right? I mean, this phase kind of makes things obscure because I have this funny coupling of the fermions and the axions, but I can eliminate it by doing this field redefinition. But again, because of the chiral anomaly, when I do this field redefinition, I pick up the extra piece from the measure of the path integral, and I get this exponential here that's now alpha f wedge f, right? So now this mass here is a real function of r and theta. This is just an ordinary functional determinant. In principle, I could do that functional determinant. I would find, some non-trivial potential for the axion field, et cetera. But the thing that actually matters is that I pick up this chiral, this piece from the chiral anomaly now involving alpha. And again, alpha here is this complex function of m and f. Okay. And so as in the massless case, I do the same kind of manipulations. I just ask, okay, if I perform a gauge rotation on this thing, do my integration by parts, perform the thing, I do integrate by parts again, I get the same sort of thing, right? The question comes down to, is this piece, d squared alpha, single or multi-valued? I mean, what is the topology essentially of this guy? And does it have some non-trivial winding, or is this just zero? If it's single valued, then this is just zero and everything is gauge invariant, and that's the whole game. But if it's multi-valued, then I have an anomaly, and so then you expect to have zero modes. And so now I can just plot alpha for different values of the mass relative to mu. And what you get is here for zero, I have this value. And so here you see at one value of theta, it's pi. And at the other value of theta, I go 0 to 2 pi, and here it's minus pi. And so this is, it's multi-valued. This is the topological instruction to doing this, is that I have this multi-valued function. And so there is no way that I can just say d squared of alpha is 0 here, right? So that's in the massless case. That's what we saw before, and that's why you have the anomaly and why you have zero modes. Now, as I add that mass, I turn it on. I can crank up the value of m, and I still have this orange curve here that interpolates. You see here at 0 it approaches plus pi, at 2 pi it approaches minus pi on the opposite side. So it's still multi-valued, and so I still expect to have the fermion zero modes. Precisely at mu, where the mass that I've just added in by hand crosses the Yukawa mass that you get from the string, this picture starts changing. And here this function approaches different values. To some extent, that's because this limit is not very well defined. But at 1.2, once I pass that value of mu, now you see this thing turns over, and at both 0 and 2 pi, it just approaches to 0. So this red curve here is a single valued function, which means that d squared of alpha is 0, as any single valued function on R2 is. And so in this case, in the red case, past this, there's no anomaly inflow, and there's no need for the chiral zero modes to exist. So I really do have this critical value of the mass here, where I have the zero modes. Yeah.
Is it easy to see that the imaginary part of alpha goes to 0 as r goes to infinity? Or You can just say, take your word for it, because it's not easy.
Yeah, I think take my word for it. But yes, yeah, I think if you stare at these equations long enough, it all kind of makes it all kind of makes sense. They're ugly looking, but they're relatively simple equations. Yeah. Good. So I expect these zero modes to exist for all masses smaller than this Yukawa mass. And now as a final check, I'm going to solve for their profiles numerically, doing the equations of motion. So I'm not going to bore you with all the details here. It is kind of a fun exercise to see how you do these things. We use what's called Chebyshev interpolation. But essentially, you're just discretizing the differential equations onto a particularly convenient set of basis functions, and then you convert this this big differential equation into an algebraic matrix equation for all of these things once you've discretized everything. It's a cool exercise to do. It's also fun, and it gives you these things. These Chebyshev polynomials are really kind of incredible for doing collocation and getting these numerical solutions. But now I can just plot what these zero mode profiles look like in 2D. And so here, this is the massless case. The profiles are again just localized to the string core that I've put right here. And now as I dial up the mass, you see that they go from being perfectly cylindrically symmetric to start to take this funny shape, right? And now as I keep cranking up the mass, you see that they, again, now the core of the profiles are not actually even right at the core of the string, and they're starting to delocalize and spread into across space. And as I approach M, closer and closer, these things stretch out and are really, really delocalized from the string along the x-axis. And the x-axis here is just because of the phase that I've kind of chosen implicit in the Lagrangian. Okay. So as I approach the critical value, these fermion profiles delocalize, and you get these really strange looking solutions for these zero modes. And so it's useful to kind of study this critical case. You can study it analytically. Far from the string, you can write what the math term in the path integral looks like. And this vanishes along the x-axis at r goes to infinity for m equals mu. And so, it makes some sense that I can think about the fermions propagating freely along the z and the x directions. And so I can search for, again, these zero modes explicitly and actually find these profiles that agree exactly with this kind of intuition that I really do have these zero mode profiles that can propagate, now not along the string, but along this whole plane extending from x equals 0 out to infinity. And so that's these zero modes delocalizing from the Axion string. One last bit of fun, since I have these zero mode profiles solved for analytically, I can look at what the effective theory on the world sheet looks like. So I have this string, and I just put it in the background of a 4-dimensional gauge field and study kind of what the interactions of these things look like from the perspective of some observer that lives on the string. And so again, the zero modes interact with the gauge field through an ordinary electromagnetic interaction. But now I plug in these profiles, and here mathcal f is essentially just the big F plus G, et cetera, numerically solved for that I had earlier. And these chi's are 2D fermions that are just localized to the string. So I take my 2-dimensional theory, I'm writing down 2-dimensional fermions, and I just have this profile, 2-dimensional fermions interacting with a 4-dimensional gauge field with this profile. And essentially what happens is now for long wavelengths, I can look at this effective field theory and organize these interactions as higher multipole moments. And you can kind of see what you expect to happen from looking at these profiles. For the massless case, you expect there to be no multipoles. These are just, there's just a monopole interaction with the fermions on the string. But as I go from here, it's clear that I'm going to have some higher multipole moments. And so you can solve for those from these profiles. And expand this whole thing in this 2D world sheet effective field theory, and then ask what the Wilson coefficients of these things look like. And it really, this is just to kind of tie everything together. As you approach the critical value, these multiple coefficients blow up, and it really is sort of a case of this effective field theory that I'm building in the IR, predicting that the whole thing breaks down. And of course, it's breaking down because these fermions are no longer confined to the string. They can propagate along this whole wall. And so I have this kind of interesting thing that's exactly how I expect things to work in the EFT. Okay, so that brings me to my conclusions. So hopefully what I've convinced you is that these these Axion strings, they can have these interesting superconductivity properties. And the main result of our paper was just to demonstrate really explicitly that the superconductivity persists even if you break the PQ symmetry explicitly with some mass term. But there is this interesting kind of critical phase structure of this mass value. And at the critical point, essentially you have this interesting behavior where the zero modes delocalize from the string, and it's in the direction of the PQ breaking domain wall. So this is sort of, again, I said that this is sort of the minimal first step that you could take away from kind of the simplest story of Axion electrodynamics. And so it leaves a lot of, open questions about how, maybe you could realize this transition, at finite temperature from the Debye mass. If this kind of has any interesting interplay in these models with electroweak Axion strings, and if this can kind of change any of these stories about how the cosmological history of Axions and Axion strings actually works. And that's all I had. Thanks very much for your attention.
Questions?
So what happens after the mass exceeds the Yukawa mass?
So once it exceeds the Yukawa mass, essentially there's just no more zero modes. If the mass is greater than, again, this, saying I'm tuning this mass, the mass is just some parameter that just exists. But if the mass parameter is greater than the Yukawa mass, there just aren't any zero modes. So you can still have the string solutions, those still exist. They're just topologically stable solutions. But the fermions don't care. They just propagate around in space-time with a mass everywhere.
Like what's the difference between this Yukawa mass and mass term? Are they not both the mass of fermion?
They're both the mass of the fermion, but they have very, very different origins, right? So the Yukawa mass is really, it's coming from the fact that I'm working in the background of the string. And so there really is, the Yukawa mass is not, the Yukawa mass of the fermions is not mu everywhere. It's only mu asymptotically far away from the string, right?
I see.
When I'm near the string, the scalar field has, a different expectation value. And so it only sees that part of it. Yeah.
And from like the beginning, it seems like Axion looks like Higgs field here. Like it's just a scalar with spontaneous.
Yeah. Oh,
potential.
sure. So the Axion field, you should think of it as, so you can't do it in the minimal standard model. But if you, in general, the Axion would be the angular component of a complex Higgs field. In the standard model, that pseudo-scalar piece doesn't exist because there's a gauge symmetry, and so that the Axion, there is no Axion to be eaten there is no Axion field that can stay massless. There's no Goldstone boson. If you take not the standard model, but the standard model with two Higgs doublets, then there is an additional Goldstone boson, and then that was actually the original Weinberg-Wilczek Axion. Was a 2 HDM with a PQ symmetry.
I see.
Yeah.
I see.
Yeah.
Thanks.
Yeah.
Just curious. This is maybe did people study? This is very nice. I'm surprised that this had not been studied before. Something else that I would have guessed would have been studied before. If you take this setup and instead of the does this make sense? Does it make sense if you try to weakly gauge the U1 instead of you again might think that if you take the gauge coupling to 0, you should somehow recover this. Does that make sense, or doesn't work because do you have an anomaly? I don't understand. How does that work?
That's a really good question. I'm not positive off the top of my head how that works. I guess my worry would be that if you weakly gauge it, essentially this anomaly inflow thing is converting to some extent the chiral anomaly that I have into a gauge anomaly on the string in the absence of the zero modes, right? But the zero modes kind of compensate that gauge anomaly. So if I'm weakly gauging the PQ, this chiral anomaly is a problem.
You have a gauge anomaly in the bulks, and so
yeah,
the gauge coupling goes to 0. the effective UV cutoff of that theory is going to zero, I guess.
Right. And so it's trickier. But there's probably some somewhat consistent story you could put together about. I mean, I don't know. I would have to think about it more, but that is interesting. It also wouldn't surprise me if some notion like this did exist, you know, in the string literature, in the more formal literature or something somewhere, you know, that someone had looked at in the 90s, or something. But yeah.
I thought Komargodsky has a paper where he discusses.
Yeah.
Okay.
Yeah.
All right. Well, go ahead.
In the axion that solves the strong CP problem, you precisely want these kinds of effects to be small, though, right? Because there you need the PQ symmetry to be almost exact. So
Yeah.
maybe that's part of the reason people hadn't studied this.
I think that's right. I mean, yeah, exactly. So in this, I mean, I didn't really emphasize it as I want, except for, you know, one kind of side comment, but this is not a very good looking phenomenological model for the QCD axion, because I break this PQ symmetry, you know, badly, right? And it's really, I mean, it's just generally the scalar, the fermions are going to get a different potential. The axion is going to get a completely different potential. It's not going to look like this. So I think the only way it would work is if there is some sort of non-minimal story in the early universe or something, where you kind of pass this phase transition before kind of going down to the more standard looking picture. Or I don't know if this happens in some kind of very non-minimal dark sector or something like this. But yeah, that's definitely true. That this is not what the story would look like for the QCD axion.
Well, I mean, you could look at it the other way around too. I mean, this is saying that the superconducting strings are more robust than the solution to the strong CP problem. I mean, in fact,
Yeah.
If you really want the axion to solve the strong CP problem, you have to solve the so-called quality problem, which people never talk about, because what it really is engineering an approximate CP symmetry. And so if you admit that, then the axion doesn't look so different from Nelson bar type models. And and you need a lot of, generally that requires some amount of model building. But if you just don't do that, then what you've shown is that these things are robust all the way up to where the explicit breaking is of order, the spontaneous breaking. That's pretty robust. So it seems like the superconducting strings are way more robust than the axions that originally motivated. I mean, that's
I like that perspective. And I mean, I had my one slide that this is the lore I get from Matt and Gigi over here, of course, is that you shouldn't think about axions as, you know, things that solve the strong CP problem. I mean, that's nice, but they're periodic scalar fields, right? And this is phenomenology that exists for a periodic scalar field, regardless of whether or not it has anything to do with you know, the theta term in QCD or whatever. And so they're scalar fields. They're you know, you can have periodic scalar fields. They show up all over the place, and they can have fun, interesting phenomenology. Yeah.
All right. Well, thanks, Sam, again.
Yeah, thank you.
Yep, great. Thanks very much. Hopefully I'll get